In this video, we're going to talk about how to add and subtract rational expressions. And what we're focusing in here is an idea from elementary school about the difference between the greatest common factor and the least common denominator. So please remember that when multiplying and dividing, you use the greatest common factor. Why is that important? Because greatest common factors allow you to reduce functions, allow you to cancel parts of expressions, where the least common denominator, which is needed for addition and subtraction, actually makes the problem larger to allow combining of the numerator. So if you need to see more information about those two things, there's a video that I made in the first section that covers the difference between what they are and how to determine and calculate them. So let's take a look at our first elementary school example. And keep in mind that when I take 7/9 and add 5/3, it's really like adding 7 1/9, right, to 5 1/3. Now, why is that important? Because that's impossible because they're not the same quantity. Like speaking in algebra, this is like taking 7x and trying to add 5y to it. They're not like terms. 1/9 and 1/3 are not the same quantity. But unlike in algebra, you are able to make them the same quantity by using a least common denominator. And that least common denominator would be 9. Now, why is the least common denominator 9? To make it short and easy, the least common denominator is the smallest number that both of the denominators divide into. So both 9 and 3 divide into 9, making it the smallest number they evenly divide into. So what I need to do now is I need to turn this thing into an expression that has a denominator of 9. I do that by multiplying this by 3. Basically, what is it missing to become 9? 9 is 3 times 3, so this one's missing a 3. And then I multiply this numerator also by 3 because that is the identity property. What I'm really multiplying by, when I multiply by 3 over 3, I'm really just multiplying by 1, which does nothing to the numerical value. So now I'm going to rewrite this as 7/9, right? That doesn't change. And then plus 15/9. And you can now see that I have the same exact value for this part of the problem, but now I have the same quantity. Now I am adding 7 1/9 to 15 1/9, and that will come out to 22 1/9. Now, the way you learned it is you keep the denominators the same, so it would be 9, and then you add the numerators. 7 plus 15 is 22. However, again, what we're really doing here is taking 7 1/9. Think of that as like 7x, right? That's 7 1/9. And then we're adding 15 1/9, and that will come out to 22 1/9. That's why you keep the denominator the same, if you've ever been wondering. That was a lot of explanation, a little bit too much for an elementary school student, but for a high school student, it's important because of what we're about to do here. So you might already be able to tell from looking at that example that this example has a very similar process. We need to multiply this by x minus 3 so that when I FOIL this together, I will have the same denominator as that. Now, if you don't see why, the first step in any problem is to factor. So if I factor this one out, I see that I have x plus 3 and then x minus 3. And again, how did I factor that out? Well, the middle term is 0x. So what factors of 9 will subtract to give you 0x? 3 minus 3. And so you can kind of, like I always tell my students, put a check mark by what you have and then put a box around what you are missing on the other term. This term has the x plus 3. It's missing the x minus 3, so that's what you have to multiply by to get the least common denominator. So what you're going to do is you're going to leave the first one exactly the same, just like we did with the 7/9 here. I'm not going to touch this one because it already has everything it needs in terms of the common denominator. And you can just write it as, a factored expression, or you can put it together. Most teachers tell you to leave it factored just in case later in the problem something cancels. So I'm going to leave it factored. And then over here, I already know, right, that this will be the same because I just designed it so that it would be the same. All right. And then what happens on the next part is I now need to either box this up or FOIL that together. We've been doing the box method quite a lot this year. But some kids, if you have a binomial times a binomial, maybe you just FOIL it out. But we'll be consistent here. So this is x squared minus 3x plus 5x and then minus 15. So I'm now going to put that into my numerator here. which gives me x squared plus 2x minus 15. And so now what I'm going to do is, again, here I had 9s, and so I just combine the numerator. So here I'm going to have this larger, more algebraic expression of x plus 3, x minus 3, but I'm going to add together my numerator. Just like here I added 7 and 15, here I'm going to add all of my like terms. So the x squared does not have a like term, so we just write it down. But my next like term would be this x and this 2x, and so that would give us 3x. And then my next like term in order from the polynomial order we learned in the polynomials chapter, we're now going to look at the constants, and they would combine -4 and -15, make -19. And so you actually are done with this problem because this doesn't factor. If this factors, you have to factor it and see if it cancels. Okay, so that is the answer, except we always have to include domain restrictions. The domain restrictions would be that the bottom can never equal, right? X could never equal -3 or 3. So if this ever happens, you can just write plus or minus 3. And again, to remind you how to find domain restrictions, you set the denominator not equal to 0, and you solve. It can, since they're all the same, you can just pick one. They're all going to give you the same domain restrictions, including the answer. So if you do that, this one would give you -3, and this one would give you 3. Now, that being said, if you were to look at a multiple choice assessment, at SOL and SAT, any of those things, they would probably foil that together. So the reason that's important is because I don't like it when students do the problem 100% correct, and they can't answer a multiple choice question because they don't see their answer. So they're likely to box this up or foil this, but you already know what it is because it's up here. So that would be x squared minus 9, and then we would include the domain restrictions. So for practice, when you take our summative assessments, you know, some of them I might go ahead and, sorry, I forgot to put the doesn't equal there, doesn't equal. I'll probably go ahead and do that on some of the multiple choice questions later on our summative assessments. Okay, so that's the idea of what happens if the least common denominator is present in the problem, which in this case it was. So what happens if the least common denominator, and by the way, sometimes they just ask on a multiple choice test, what is the least common denominator? And so just to remember that the least common denominator for this problem would be these two things. It would be x plus 3, x minus 3, otherwise known as x squared minus 9. Sometimes on some multiple choice tests, that's all they ask for, actually. Okay, so what happens if the least common denominator is not present in the problem like this? Like, what number do 15 and 12 both divide evenly into? That's a pretty complicated thing to try to figure out. So what you do is you actually factor these problems using your multiplication tables and try to find something they share. So when you think about it like that, it's pretty evident that this is 3 times 5, and this one is 3 times 4. And so what they have in common, right, what they have in common is that 3. And so that's what you don't need to multiply by because they already have it. I like to explain this like, you know, if you have a sibling and they open presents, you are not going to want what they have that you also have. You're only going to want the present that you're missing. Like if you guys, you know, if you have a brother or sister, or you know, and you both have roller skates, you're not going to envy the roller skates. You're going to envy the present that you don't have. So both of these problems share this 3. They don't envy the 3 because they have one. What they envy is the one they don't have. This one right here, it wants the 5, so it can be like the other one. And this one right here wants the 4. And now you can see that we actually have the exact same denominator. It's out of order, but we have the same thing. So once we figure that out, we just multiply the numerator by the same number that was missing on the denominator, right? The 5 divided by 5 is not going to do anything because that's going to be 1, and the 4 divided by 4 will be the same thing. So then we rewrite it, right? So we rewrite this, and 3 times 5 is 15. 15 times 4 is 60. And you can see also here that 3 times 4 is 12. 12 times 5 is also 60, so we have a common denominator. We're going to be subtracting in this case. This would be 8, and this would be 25. And again, if you were to reduce these two fractions, you would go back to the original problem. So have a common denominator of 60, and 8 minus 25 is negative 17. Now, keep in mind that that negative is on the numerator. It was originally in the middle. The best way to do that is to put it right in line with the division sign. That's where it will often be on a multiple choice test. So using that same idea of looking at the multiplication tables, we're going to do the same thing over here, but we're going to factor. And this is why factoring is just so important in Algebra 2 and beyond. So same thing we've been doing. Take factors of 15, move this way, and subtract them until you get 2. Well, those factors would be 3 times 5. So we're going to write them like this, 3 times 5. And then we're going to attach the negative sign to make this positive. So we want to attach the positive here, the negative sign to the 3, because negative 3 and 5 make positive 2, but they multiply to 15, and those are our factors. Here's the good news about understanding how this works in this chapter. One of these factors has got to be an answer over here, and that's helpful to students, especially when the factorization can be, more challenging. So in this case, we're moving this way. We're taking factors of 12 that are going to subtract to give us 1. That's a common factorization. That is 3 and 4, right? So you can already see the 3 appearing again. So we're going to put our 3 here and our 4, and we're going to attach the positive sign to the 4 so that we get a positive 1 here and the negative sign here. And then as promised, you can see that they both share this. So they both share the common factor of x minus 3, right? They share that common factor. So again, this problem here wants what it's missing. It's missing the x plus 4. They want what they don't have. Just like, it's almost like human nature. So whatever I put on the bottom, I put on the top. Okay. And then here, this one is missing the x plus 5. So I put that on the bottom. And then I put it on the top. And just like in elementary school, dividing an expression by itself gives you 1, so it doesn't actually change the problem. So now I have on the bottom here, I have these 3 expressions. You do not repeat, do not have to FOIL this together. And even on a test that I make, I mean, if it's a binomial, sure, but having to multiply 3 binomials and get some kind of, complicated expression, there's no way I'm going to make you do that. So just keep these factored out. Okay, so just keep those factored out. Maybe just make a list of them. Maybe put them in order. I did not put them in order. I will at the end. Actually, this one's in order and this one's a little maybe out of order, but you can just see that they're the same. That's what matters. And then up here, you need to multiply these together. And maybe this is the time to move beyond the box, especially for binomials or beyond foiling. I'm going to show you a quicker way to do this. What you do is you multiply these two. Right, and this is what the box does, which is x squared. And then you multiply these two, which is 8. And then you simply add 2x and 4x, which is 6x, right? I mean, that's what the box does. Now, if that makes you feel uncomfortable, then box that up. Okay, but over here, we would have x squared. Here we would have negative 20. And then we would, in this case, take negative 4x and add 5x, which would be plus x. So now that we've done the box for many, many chapters, I'm kind of just doing the box now in my head. Again, I'm just adding those 2 terms together, and then I'm multiplying the first and the last term. Now, what's extremely important with subtraction, it doesn't really matter in elementary school because there's only one number, but in high school, you have got to distribute the negative to all terms. And we started talking about that back in the first unit. And one of the hints that I gave you back in Unit 1 is when you distribute a negative is to rewrite it, so negative x squared minus x plus 20, and then basically scratch out the rest of the problem. Now, why is that important? Because you might accidentally subtract part of it, not all of it. So again, we started with subtract this expression. If I distribute that and then rewrite it, I'm going to want to get rid of this so that I don't get confused. And so now all I have to do is combine like terms like I did with the addition problem. So I have x minus 3. I'm going to put the 4 numerically next, and then x plus 5. Okay, and then I'm going to combine my like terms one at a time. X squared minus x squared would be no x squared. So if I take this and add this to it, it would cancel. If I take 6x and I add negative x to it, I'm going to have 5x. And then if I take 8 and I add 20 to it, I would have 28. And these problems routinely will factor again and cancel with something. In this case, they did not. But routinely, imagine if this was a 25, right? I would have to factor that 5 out, and it would cancel with something in the bottom. So just be aware of that happening sometimes. And this is, in fact, your answer, other than stating your domain restrictions. And again, the way you would do that is you would set all of these not equal to 0, and you would find that you would have -5 can't be in the answer ever, or -4 and 3. And many of you, I remember when I learned this, I was like, what are those domain restrictions? We're going to be talking about domain restrictions when we do graphing. They also matter when we solve, but they're going to become clearer what they are when we graph. So just keep that in mind. The explanation of what these are, they actually have specific names that will come when we do graphing.